by viewer request. In this video we're going to prepare hydrazine sulfate starting from household bleach. There are a few other good videos out there which showed how to make hydrazine, but none which showed this method using urea, and this one is a bit more OTC, although the yields aren't as good. We're starting with 500 ml of 5.25% sodium hypochlorite bleach. Get the cheap watery stuff with no thickening agents or detergents in. We placed our bottle of bleach in the fridge for a few hours to get it nice and cold, and now we've transferred it to a large 1-liter beaker with a large magnetic stir bar in. Note: if this is the first time you're doing this reaction, we recommend starting off with a smaller quantity and using the very large beaker. We'll explain why later. Temperature is at about 7 degrees C, so nice and cool. We've weighed out 32 grams of solid sodium hydroxide. This is around the 2.2 molar excess to the sodium hypochlorite we're starting with. The reaction itself requires 2 moles, however it's very important to keep the reaction mixture strongly alkaline, so we use a bit extra in order to make sure it stays this way. With the temperature nice and cool and the stirring going strong, we now add half of the sodium hydroxide to the bleach in the beaker. As the sodium hydroxide dissolves, it's going to release heat. Too much heat and the bleach will decompose and disproportionate, reducing our yield. But below 20 degrees is pretty safe, and we got up to about 18 here. Let the mixture stir until you've got a nice clear solution. Now we're going to chill down the bleach mixture again until it's back down to about 7 degrees. Cover up the beakers, and make sure that the rest of the sodium hydroxide isn't exposed to the atmosphere, otherwise it will absorb water rapidly. While we're waiting for this to cool down, we can prepare our other reagents. We've weighed out 0.75 grams of powdered gelatin. This is regular baking grade gelatin, the same gelatin that we use in our cake recipes. Exactly what it does is not completely known, but it's thought to chelate any tiny amounts of metal ions such as iron which might exist in the reagents. Metal ions catalyze the decomposition of the hydrazine, and so this helps to prevent this. Apparently using calcium hydroxide also works, but we've not tried it. Okay. Here we've got the beaker of distilled water which we warmed up. It's very important to use distilled water. Tap water will ruin your yield due to the metal ion content. The trick now is to use the minimum amount of water possible. Our product is water soluble, so we want to keep the liquid volume to a minimum. First we dissolve the gelatin in about 15 ml of the hot water. It takes a bit of stirring to get a clear solution. Here we go. Now for our next reagent. Here we've weighed out 22 grams of urea crystals. This is a very slight stoichiometric excess to the sodium hypochlorite we are using. We're not 100% sure about the concentration of the bleach, so using a slight excess makes sure all the hypochlorite reacts. In theory you can also use ammonia for this reaction, but in practice the liquid volume becomes too great. Now we're going to use the warm distilled water to dissolve the urea. We want to make up a saturated solution using as little water as possible. As the urea dissolves it cools, but with a little warming we got everything to dissolve, making up about 40 ml of liquid. If the mixture cools too much and the urea won't dissolve, then put the beaker in a microwave for 10 seconds. Okay, here's our urea solution and our gelatin solution. Add the gelatin to the urea and stir to form a homogeneous mixture. And now reserve this at room temperature ready for the reaction. Here's our bleach and sodium hydroxide mixture chilled down again. The temperature is around 7 degrees C, So we're ready now to add the rest of the sodium hydroxide to this. Make sure the mixture is stirred well so no local hot spots develop. Temperature rises to about 17 degrees again. Perfect. We're now ready to do the reaction. As we said before, if you are a hydrazine virgin, or if you are using reagents of unknown purity, we recommend doing this on a small scale with a beaker that can hold at least 3 times the volume of your bleach mixture. If anything goes wrong or you have impurities present, side reactions are going to produce a lot of nitrogen gas, and this is going to cause the mixture to foam enormously. How much foam you get is directly proportional to the quality of your reagents and how much the hydrazine respects you as a chemist. But note that if you get no foam at all, then your bleach is probably old and useless. Dial up the stirring to as high as you can for the reaction. And now in one go, add urea and gelatin solution. The mixture turns white as tiny bubbles of nitrogen gas are generated in the mixture. Note that the foaming can be delayed, so don't get too cocky just yet. We've got some gentle foaming, but not too much, which is great. The reaction has caused a slight temperature increase up to about 25 degrees C. Soon the gas production dies down and we obtain a clear solution again. This contains an intermediate compound, which we now need to decompose in order to get our hydrazine. So we switch on the hot plate and heat the mixture quite strongly. The decomposition occurs above about 70 degrees C, but you get best results if you heat to above 85. Temperature increasing. It's a smart idea to cover the top of the beaker with plastic wrap. Hydrazine is quite volatile and you don't want it escaping as it is formed, as you will get a lower yield. In addition, it is highly toxic and known to be carcinogenic. So you really don't want to be breathing this in. For the technically minded, here's a simplified reaction schema, very similar to the Hotman rearrangement. As the temperature increases, the mixture starts to foam again due to some product decomposition. Hold the mixture above 80 degrees C for 5 minutes, then remove and allow to cool down. Keep the plastic wrap on and chill the mixture down to close to 0 degrees C. As the beaker cools right down, you may notice some small white crystals forming on the wrap and on the sides of the top of the beaker. These rapidly melt when taken out of the freezer. This is actually pure hydrazine which has evaporated and frozen. Don't try to isolate this or distill it off, because it's very toxic and can be dangerously unstable. Here's our reaction mixture chilled down to just a few degrees C. For the next step, we're going to need lots of 50% sulfuric acid in water. That's 50% concentrated by volume. So make up the batch of about 100 ml using 50 ml of water and carefully adding 50 ml of concentrated sulfuric acid. The temperature will go above 100 degrees C, so take care, and then chill the resulting liquid in the freezer until it's at 0 degrees C. You'll need about 60 ml of acid for this first step. Get the chilled reaction mixture stirring well. And now slowly add the chilled 50% sulfuric acid to it. To begin with, the acid is going to neutralize the excess sodium hydroxide that was present in the mixture. So there's not much effervescence. But once this is complete, the acid will start to react with the sodium carbonate that was formed as a reaction product. And lots of CO2 is produced. So go slowly so you don't risk creating the fountain. towards the end of neutralization. The effervescence lasts a while, so allow the mixture to stir and get rid of the Co2 gas. After about 60 ml you will get to a point where acid addition no longer generates effervescence in the mixture. At this point measure out an additional 40 ml of 50% sulfuric acid. This is enough to convert all the theoretical yield of hydrazine into its sulfate salt. Note that this is the hydrogen sulfate salt, so it's a 1:1 molar ratio. Let's get stirring on, and we'll add this to our mixture. The mixture turns cloudy and little tiny snowflake-like crystals start to appear in the mixture. Enjoy watching the crystal form and settle. This is our product, hydrazine sulfate. The temperature now is around 30 degrees C, so we'll now cover the beaker and chill it down in the fridge in order to maximize our precipitate. Just be careful not to go below about 10 degrees C, otherwise sodium sulfate can start to precipitate out. At about 15 degrees the precipitation is largely complete, so we filter at this point. Dry the product really thoroughly on the pump until it's light and fluffy. Here we go, our final product. This is 22.6 grams of hydrazine sulfate as pure white dry fluffy crystals. This is a yield of 49% on the starting hypochlorite, assuming the solution was at the strength written on the label. This is not bad at all, and the alternative kerosene process typically gives about the same sort of yield. But do note that the reaction we've shown you here is not forgiving when it comes to purity of reagents. Well, we really wanted to claim a yield of over 50% for this method, and 49 doesn't quite cut it. But we do have a final trick up our sleeve. Here's the filtrate left over from that final filtration of the product. This still contains some hydrazine sulfate dissolved in it. We've weighed out 20 grams of anhydrous copper sulfate here. It's a white color because it's the anhydrous salt. And we've got about 80 ml of water. Let's add the copper sulfate to the water and stir to form a saturated solution. Looking good. Now add this to the filtrate. You can see a turquoise blue color forming in the mixture. Cover and leave this for an hour to react. You'll see a fine light blue powder forming and settling in the beaker. This is a compound which is an adduct of copper sulfate and hydrazine sulfate. So we filter this. And get it really dry until it forms a fine powder. And here it is. An extra 6.9 grams of the copper sulfate and hydrazine sulfate adduct. This is an extra 24 millimoles of hydrazine, which takes our total hydrazine recovery and yield from this reaction up to 56%. Not bad for household bleach, urea, sodium hydroxide and sulfuric acid. All cheap ingredients,